Hi everyone. In today's video, we are going to go through some of uplink throughput enhancement features. We'll dive into around 10 uplink speed posting actions. So let's go move forward. So initially, actually, this is the context of today. We're going to explain about the uplink data aggregation, uplink fallback. This is mainly concerning about the 5G non-standalone. Then one feature is called uplink intercell interference randomization, and also we'll be going through the proactive scheduling or the pre-allocation for the 5G, like what is the kind of improvement we can do through tuning this feature or disabling this feature in the uplink, and also we'll deep dive into the details of this particular feature. Then we'll be speaking about the 5G uplink multi-user MIMO, and we'll be speaking about usage multiplexing. Then we'll go through uplink 256 gram and usage wave form adaptation, and these two features I already explained before. So this one I will be referring to the previous videos, and at ending will be resulting in something called ad hoc actions, and can be some of the actions which can be done in particular scenarios, and also like this is have some dependencies on the configuration of the network, or even sometimes different vendors can support different functionality. So moving forward, the first feature here, it's about the uplink data split or aggregation. You can say uplink data split or uplink data aggregation. What it means by this. Okay, let's see in this feature description figure, the figure in top left here, the first figure. Here it is showing that without uplink data aggregation, what will be the scenario. So in case we have the master cell group is an OR option, so this means we'll have the uplink throughput for the 5G, for the 5G NSA will be mainly transmitting through the 4G, or if it's SCG, for example, so this will be mainly transmitting through the NR. So here where the uplink data aggregation is coming to the figure. So in this case, you can combine both 4G and 5G leg to have a higher speed, and this can be combined as shown here in this figure. And now the user can combine both of them and to send higher speed to the 5G, to 5G node B. And here, this is how the things is being done in the layer wise. So assuming here, for example, that we're using this SCG, so our primary path will be, our initial path will be through the SCG, through the secondary node. For example, as you is showing here, you having like two nodes, two legs, one for the 4G and one for the 5G. And again, this is NSA. So initially, the UE will be transmitting the data through the uplink till reaching into RLC layer, and after they have the aggregation, I mean, so and here you will be transmitting until the RLC, then both RLC, the BDCP of the SCG layer or the secondary node will be aggregating the user plane for both from both legs. Now it will be aggregated into the BDCP, so we'll have now higher speed because now we are combining the speed coming from 4G plus the 5G. So how to verify this from even the drive test logs or from the traces in general? So in general, like not all the UEs are being supporting this particular feature, as you can see in the bottom left here, that from the UE capability message information, especially for the NDC or MRDC, you need to log into the UE capability, log into this particular section called general parameters. Under this part, you will find this split DRB with uplink both MCG and SCG supported. So if this one is not included or it's showing not supported, this means uplink data split is not working for this particular device. So you need to verify this message before doing any drive test. Now, speaking about how this in general, it will be triggered from the UE, how the UE will be triggering this one and based on what. Actually, simply it's based on one of the parameters that's being configured from the GNB side and delivered to the UE through the RS reconfiguration message. This parameter, for example, it's called data split threshold. So, for example, if the buffer of the UE size is larger than this particular parameters, which you can control it through the GNB, so in this particular case, the UE will start the data splitting through the both legs as mentioned here. So, for example, here, if you look into the RC configure message, you will find two things here, something called cell group. If it's, for example, one, this means you have initial path through SCG, and this is also configured. And here is the data split threshold, which is here you can see is, for example, in this particular example was 1,600 bytes. And the main idea here that the higher the value, the less the data splitting or less data aggregation, the lower the value, the more data aggregation. So this is depend on your network usage. You can just try to tune this parameter. Usually they define it for lesser value as much as possible, but not very less. But so just to be able to get the gain of the data aggregation, especially for the high or for the heavy users. Now going for the benchmark results, you can see here the blue figure without data split, it was getting around average 82. after data splitting, after adding additional leg, both legs data aggregation or data split, now we can get up to average 145. Now moving forward, the next feature it will be about the uplink full 4G fallback, and this is mainly applicable for non-standalone, as I mentioned. So what did this would do? Actually, the main idea of this feature that the uplink data path will be mainly transmitted through the 4G leg. Whenever you have a poor uplink SNR or uplink coverage for the 5G, so in this case, you can get the benefit of having, for example, non-standalone. For example, you're having FDD network, it can have a better performance on the uplink, so you can switch off. So if you can see this figure, for example, assuming this particular user he's under the site, nearby to the site, so in this case he's enjoying, he can have a good coverage for both uplink and downlink, so he can have both uplink and downlink through 5G site. Now assume that you have this user is moved to the edge, or you have edge users where this the only downlink coverage is being reachable, or we can say in other words, more specific, that the uplink coverage of the NR is very poor, and this particular scenario, it's better to enable this feature to enable the fallback towards the 4G leg in order to get the gain of the, for example, FDD network, which is might having a better uplink performance for the edge users. I'm just for simplified way, I show it here as two different sites, but usually we'll have it within the same site, but the 4G coverage would be extended in the uplink higher than the 5G. So for example, here, as you can see, this particular user is still receiving the downlink through the 5G node. However, the uplink is being transmitted through the 4G leg. This is the main idea. So if you look into this figure, this is like whenever you have a good coverage, so the transmission for uplink downlink data will be through the 5G leg. But assuming like for the uplink, you can see uplink data and SRS PUCH transmitting, it will be mainly through the 5G leg, which we are here. Once you move to uplink poor coverage, so what will happen in this particular case? Uplink data will be through the 4G, but still you will have the SRS and PUCH reporting. It will still being done through the NR. So you are only focusing data fallback, or uplink fallback is mainly for the uplink data. How you can check and verify this from the signaling point of view? First of all, you need to know that you have a parameter from the GNB side. This parameter, for example, it's showing the uplink SNR. So uplink SNR for BUCH especially, what would do, like for example, if you setting this parameter to 10, the GNB know that this parameter is 10, so it will monitor the uplink performance for this particular user. And if this particular user, for example, is falling below the threshold, which is 10, let's assume the user having 5. So in this case, what will happen? The GNB need to deliver the configuration to instruct the UE to make the fallback. So how this can be done? This is initially same as the figure we showed in the previous slide, that was showing that, for example, you have the data split thresholds was around 1,600 bytes. The initial path, and this is the most important, was SCG. So once this condition is being achieved, so this RSG configuration will be delivered again from the inode B to the UE to instruct him to only use the 4G leg. So it will disable first of all the data split. It will make this value into infinity, and it will change the cell group from 1, for example, to 0, to advise the user to start using the 4G leg for the 4G transmission, uplink transmission. And here's just a quick summary for the speed performance. For example, once we disable the feature here, you can see you have a very big jump in the NR speed, uplink speed. However, just to highlight and take it into your attention, this is not really direct, like you can see here, this is huge improvement, but it's not really like that. Like the main idea that you excluded the very edge users from the 5G side. So you have actually two impact on those SKPIs. The first one, the stat itself is jumping because you excluded the very bad samples which was generated from the poor users. And the other one, that as long as you're excluded uplink users, for example, you will have a less uplink interference. So this is even having more improvement in the center users. This is the main idea. So usually when I think about the comparison of that part, I compare both FDD, which is usually a split, when the data split happening, or the fallback happening to the FDD layer. So for example, I compare what was the average, was including edge user for both layers before doing the actions. For example, here it was around 1.85 for the 4G layer, for the 5G level before doing the data split, the uplink fallback. And the FDD layer is having around 4.12. So I can assume now that the users is now, instead of getting 2 mega as an example, just like an indication only, now is getting around 4 megabit per second. And some vendors support the edge users counters for the uplink speed. So maybe you can just directly look into this counters for both FDD and NR to be able to evaluate the performance. Now moving forward, now this is a uplink intercell interference randomization. like how this feature is being working. So in general, this is the normal distribution of the resources. Looking into this figure on the left, whenever this feature is off, assuming they have 3 cells, assuming within the same site or different sites or whatever, it's okay. So assuming that now the resource allocation for the resource flux scheduled RBs was starting from the start of position of the band and is going in sequence like that for the uplink. Now what will happen? The second cell will be the same, third cell will be the same. So assuming that these 3 cells can interfere each other, right? Because the same resource block, same frequency is being assigned for 3 different frequencies. So this can have kind of uplink interference. And so it can impact your quality as well. So this feature making a randomization, and this can mechanism of distributing the resource block through different areas within each of those cells. This is, I think, it's more into the how each vendor is being operating, but this, like assuming this is the idea now, for example, the cell 1 is still initiating the resources from the start band till here, and cell 2 start from after cell 2 starting after cell 1, for example, the mid of the band, and cell 3 is the end of the band. So now you will have a much less interference, and accordingly can be reflected in your spectral efficiency, and also can improve the percentage of high order modulation and coding scheme. And here, this is the same idea, but here in terms of users, you can see all users will be allocated within the same area of resource flux. Here we have a different allocation. And just to take it into your attention as well, that this feature actually will not take effect if you have a high load in the network. Assume that all the cells are being loaded, so this kind of distribution, it's not anymore valid, because almost the cell will be utilizing most of the resource blocks. So actually, if you would like to test the scenario or try to test the gain of this feature, it's better to deploy it in scenarios where you have a lightly loaded network, for example, the PRB utilization less than 40 or less than 30, so you can gauge the gain and confirm what kind of gain you have. And in terms of heavy load scenario, this feature have no negative impact. It will not just be triggering. And this is just a quick results from 5G draft test results. We observed around 4% improvement in the SNR. We have the same feature for uplink and downlink, by the way. And here I showed for the downlink, but it was almost the same for uplink as well. And here was the MCS. It was improved from 43 to 45%. So this is about the downlink, but uplink also having the same performance. And in general, you need to evaluate MCS, downlink and uplink throughput, and average uplink interference in case you would like to gauge again. So this is one applicable for downlink and uplink. Okay, here in this section, we are going to explain in general what is the main understanding or concept of the pre-allocation or proactive scheduling feature. It's having a different name between the vendors, but at the end, this is a 3GPP feature, so you can say it proactive scheduling. So in general, let's first explain what is the concept and how this can improve the uplink throughput. So in general, you can see here in the figure in the top left, this is showing the normal scheduling, or they call it dynamic grants or dynamic scheduling in general. So what it means by that, for example, assuming that the users were already having uplink data, which is being transmitted in uplink. So once the users move after finishing or completing this uplink data transmitting, so he will move to the inactive state. So assuming that the user was moving in active state and he starts receiving uplink packets start to arrive. So in this particular scenario, the users need to ask the GNB for resources to start the uplink data transmission, right? So first of all, the users need to wait for something called scheduling request cycle. Generally, once the user receives uplink packet arrives, he's supposed to send something called the scheduling request. This scheduling request is being sent to the GNB, assuming this is GNB, in order to ask scheduling request and also buffer status report in order to ask the GNB for the resources to be allocated for this part. So this part actually is configured. There is a configuration for the scheduling request. For example, the user can be transmitting scheduling request every 20 milliseconds. So the users have to wait for this particular duration until he's able to send scheduling request. Once the user sends the scheduling request to the BTS now will allocate the BDCH, which contains the uplink grants. Uplink grants means that the resources for the uplink, and this should be informed through the BDCH channel. So the BTS or the GNB is informing the user, for example, that you will need this kind of resource blocks, and number of resource blocks, timing, and so on. So this will be informed through the uplink grants. Once the user receive the uplink grants, now it will be starting transmitting the uplink data. But here there is several concepts about the normal scheduling. First part, you need to wait for the scheduling request, right, which can be 10 millisecond, 20 millisecond. And also for the BDCH or for the search space in general, there is also configuration duration for this part. So this is also, you have to wait, the unit have to wait for this to transmit the BDCH based on this kind of search space period or duration. And also on top of all of this, if there is a high load in the site, in the unit B, or there is a high load in the BTS, there is high traffic volume or high number of users, so there might be, or there may be a queuing within the unit B side. So in this case, the users might be wait in the queue for some time until his unit B is able to assign this kind of resource. So all of this 3 points which I highlighted is adding to the latency. So this is means the latency of the uplink, especially, it might increase. And here where the proactive scheduling or the pre-allocation feature is coming into the figure. As you can see first figure here in the bottom left, this is called proactive grants or proactive scheduling without something called skipping. We'll discuss it now. But assuming the same scenario, the users finished uploading data, and after the finishing the initial data transfer, now he's supposed to move the inactive state. So, but in this particular case, you can see there is a proactive scheduling. Proactive scheduling means that the unit B will be transmitting the BDCH with uplink grants, as mentioned down here. The uplink grants will be transmitted, can be continuously and can be based on a specific period, which is being configured. For example, every 10 milliseconds, the unit B will assign the BDCH without waiting for any scheduling request. And this time, the GUI doesn't need to send any scheduling request. Unit B will directly transmit the BDCH in this particular case. But in case if the user receives this proactive scheduling, which is a BDCH uplink grants, so in this case, if the user doesn't have any uplink data or there is no uplink data to transmit, so he need to translate this into something called padding, right? So like if the user doesn't have any data to send, so it's not generate this uplink packet from padding. So actually, and the main drawbacks of this part, that this padding is transmitted, this padding across the error interface, and it can contribute for overall uplink interference. This is the main idea of the padding. So the user can keep sending the padding as long as he's receiving the proactive scheduling. So in this case, once the user, for example, receives the uplink packet arrives, so he will be able to directly transfer the uplink data. So you are saving this kind of delay which was being sent here. This was the latency. So this was the improvement which came here, that from this proactive scheduling, that it will improve the latency. So in this case, there is several drawbacks which can have an impact on the system capacity. The first part, that this padding is increasing the uplink interference over the error interface. This can have an impact on the uplink performance. Secondly, sending uplink padding all the time, this is also consumed from the uplink PRB utilization. So this can increase the uplink PRB utilization. So it can also reduce the system capacity, because this is unnecessary information. It's just padding to reply to the proactive scheduling. Third part, that as long as the unit B is sending the proactive scheduling through means BDCH, transmitting the BDCH with, for example, a certain period or continuously, depending on the BTS configuration. This is also will increase the CC utilization for the BDCH utilization. So this is having impact also in the system capacity. So this is 3 drawbacks. So the main idea here, that whenever we mention in the top here, that to improve the uplink performance, you should disable or tune the pre-allocations or the proactive scheduling. And can be done, by the way, for a specific users or even for a specific services. For example, you can keep it for Vault users, you can disable for data users, or also you can tune it if you don't want to disable it. For example, you can tune it, for example, to, for example, increase the predictability of the proactive scheduling, which is a DCH allocation. So this can reduce or mitigate this kind of impact in the interference through reducing this kind of padding tanks and so on. This is one solution. The second solution is completely disable for a particular service to reduce this kind of drawbacks which you just highlighted here. So can having an impact in the uplink throughput. And there is one feature called proactive grants with skipping. This proactive grants with skipping, actually what it do, it's the same proactive mechanism of the proactive scheduling or the proactive scheduling or the pre-allocation. But in this case, if the user doesn't have any data in the uplink, the user will not reply with padding. So the user will not reply with anything. He will just keep it like no data will being sent here. So can reduce also the system capacity, plus, the interference, plus it can also reduce the consumption of the PRP allocation, but this kind of PDCH or reactive scheduling will be there. We cannot mitigate it. So this is can have an improvement. So once a user also receives the uplink packet, he will be able to having doubling data. So this is kind of reactive ground truth skipping, like it's giving the benefits of keeping the improvement in the delay and having a little bit or to mitigate the impact of the uplink resource consumption, which is caused by the bad sending the padding whenever the user doesn't have data. And actually this feature, first of all, which is called reactive ground truth skipping, it requires two things. First of all, it required that the user itself supporting this kind of feature. How to check this part? From the capability info for the 5G, we can go through the capability issue, search for MAC parameters. Under this part, you'll find something called skip uplink TX dynamic. If it's supported, this means the users can skip the dynamic proactive scheduling. If you have the proactive scheduling and there is no data, user can skip it. The first part. Second part, there is one parameter will be delivered from the GNB to the UE in the 5G standalone through something called cell group configuration in R. This is, for example, it's called skip link TX dynamic. If it's false, this means it's not supported. If it's true, it means it's supported. And this is the main idea about this feature, but I didn't try it as a practical. It's something new for me. So maybe if I have any information about it later on, I can share it and share it with all of you. This is the main thing here. And in general, as you can see here, the benchmark results, as you can observe here, that we have improvement on the uplink throughput. Very good improvement after disabling. This was disabling, and the uplink interference as well reduced. And actually throughput improved because of two things: uplink interference reduction plus the PRP utilization reduction as well, and also the CC load was decreased in this part. Now let's move to the next feature. Now moving forward, it's about uplink multi-user MIMO feature. Uplink multi-user MIMO feature in general, as you know, it can increase system capacity by even double or even more, depending on how many layers is being supported. So if you're speaking about uplink, you can go up to 8 layers. 8 layers. So let's quickly, and this video actually you can refer to this video, my previous video in the channel, which was showing a quick explanation how the resources being really allocated and how you can do the test methodology for this, or which test process you can follow for uplink multi-user MIMO. So this is how it's being working. Assuming now the normal case scenario, whenever without having uplink multi-user MIMO, how the resources being allocated. For example, if you look into user 1, 9, 10, and 11. These users will be allocating from the GNB like that. They will be sharing the same time and frequency resources. So for example, if you have 100 RB, assume that all of them having the same ready conditions, so each one maybe will take around 25 resource block. So the resource block will be split above all of them, and this will be within the same time. So this means that the throughput will be actually limited to a certain stage. We cannot go through that. For example, if you're assuming the maximum cell throughput at this case is 100 mega, so each user will take around 25, so the accumulated value will be around 100 mega. This is just an example or an indication. So after you enable this feature, what will happen if you look into this feature, this particular users, assuming the feature is enabled now, this user is not achieving this multi-user MIMO. There is a condition. Usually it's related to having a less correlation between the users. For example, the users being distributed among the cells for different areas. For example, as I mentioned down here, the user should be located, for example, 40-degree differences in angle between all of them to have a less correlation in order to have this kind of beam allocation. If you also refer to the video I mentioned before, you will understand it more. So assuming that this user is having a high correlation, so it will not be in the pairing state. Assuming now we have multiple users, up to 8 users, for example, they are in the pairing state or the uplink multi-user MIMO, which having a less correlation and achieving the condition of the SNR and so on. So the GNB now will start doing this kind of allocating the same resource blocks. For example, each user can take the full usage of resource blocks, assuming 273 for 100 megahertz. So each user can take the full resource blocks, even within the same time, but as you can see, within different layers. So if you're assuming that you have 2 layers, 2 users being paired, assume that one of those users can take 100 megabit per second as maximum. In the normal case scenario, if another user is coming into the figure, it will be split between them 50 and 50 megabit per second. But whenever you have multi-user MIMO, so both of them can take 100 mega because they can use 4 resource blocks within different layers. So as shown here in the example on the right, this is before testing. This is from drive test results. Before doing the test, before enabling the feature, we have one user doing the test who was getting around 100 mega for cell throughput. After we enabled now, the 2 users was getting as a maximum around 200 and as average around 175 back, which almost increased the serialization by maybe the double, almost the double. And this is after decelerating again, going back to the feature, so the back normal scenario, and here touching again 200 mega. So in general, like this one, if you would like to evaluate the gain from the uplink or from the OSS KPIs as well, not only the drive test, it's usually recommended to enable the feature in the very highly utilized sites to be able to judge the improvement in terms of traffic and even throughput. And from the KPIs point of view, we have usually KPIs related to the MIMO, multi-user MIMO, which is, for example, number of assigned layers or allocated layers. You can check the average after and before enabling the feature. And also you can evaluate the uplink throughput, uplink user and thread throughput, and uplink traffic as well, because if you have a limitation in the resources, this can also be reflected in high traffic. And this is also supporting downlink user MIMO, but the downlink is supporting more layers than the 8. So as I remember, the maximum was around 16. Now moving forward, it's about the 5G VSH multiplexing with DMRS. Actually, this one I have explained it as well before, but I explained for the downlink, which is BDSH. You can refer also to my previous videos, but let me quickly explain this part with you. For example, without multiplexing, the normal case scenario without multiplexing, you can see, for example, this is the slots or symbols where you have the DMS is being transmitted. So you can see the free resources which is not being used at all. This is unused. There is no data or nothing is being transmitted here, but there is a gain of this part that DMRS can get the free power or free to increase the power by around 3 dB, so the coverage by around 3 dB through utilizing the free resources usage or power to be increasing the DMRS power by 3 dB. So this can have a very good gain, especially for the edge users. This is without multiplexing. After enabling the multiplexing, the main idea now that the free resources can now be used for BUCH transmitting. So this can increase your number of resource blocks allocated to the BUCH, accordingly can having a good impact in the maximum speed, right? Uplink speed. So usually how this one is working, it's working based on, first of all, you need to enable the feature. Secondly, you need to tune the related threshold for the uplink SNR. BUCH SNR. So for example, now assuming this is a feature here description, they use transmit the BUCH transmission. So Unit B will start measuring the uplink BUCH SNR. If the uplink BUCH SNR is greater than or a very good, for example, a particular threshold, let's assume you give the threshold for the feature around 10 dB or 15 dB, and the user is having 10 dB, 20 dB SNR. So in this case, Unit B would decide to use a multiplexing because the user having, for example, a particular or a good threshold which is being configured. So it will instruct the user through sending BDCH DCI. There is no like list signaling overhead because there is no RSU configuration method for this. It's just through the BDCH resources, and this will inform the users about the number of ports or assigned ports is being used, and the user now will consider to use multiplexing based on the number of ports assigned, and now he start the BCH transmission and he will follow the scenario. And this is the 3GPP table which showing this scenario, which whenever you have power boosting and we're using the power boosting, for example, whenever you don't have BCH. And by the way, it can be a drawback, so you have to be very careful when you assign the thresholds, that it can impact, especially if you're giving low threshold of SNR to activate the feature. This can impact the edge users because they will lose this kind of 3 dB posting. This was the main idea for BCH. Moving forward, actually, for the next features, for uplink 256 QAM, this feature actually I have explained in the previous feature. You can refer to this feature to apply to my previous videos, and you will find the explanation about this part. And also same for BUCH wave adaptation. I have explained this one as well. You can refer to my previous video, which also I referred earlier in the previous slide. Now moving to the ad hoc parameters or features. Actually, this is like, it's something it can be done in very specific scenarios, and it might not be applicable all the time. For example, there is something called CSI reporting period tuning. For example, the channel state information. Whenever the user is going to report the channel state information, there is a duration of that part. Usually it's configured as 80 milliseconds. This means whenever the user is reading the CSI, which is being transmitted from the BTS, and start to report, for example, the CQI through the BCH. So, for example, it will be transmitting every 8 milliseconds. So if you increase this duration, this means you will have less BUCH transmission. you will have, because you have less reporting CQI. For example, here total CQI reporting reduced a lot. So this was having a very good impact on the uplink speed because you reduce the BCH resources. So this can be utilized by the BOCH. So in this case, you can have higher speed. Can be done in very particular scenarios, because the main idea about this change, once you increase this kind of 80 millisecond to 160 millisecond, this means the drawbacks of that part, it can having also reflection on the downlink, because you will not have a timely update of the CQI. So the GNB can have take a wrong decision or not accurate decision. So it can also impact the downlink throughput as well. So the main idea, increasing the duration, it can reduce the BCH resources, less CQI reporting, and can improve the uplink performance. And the less CQI reporting, as I mentioned, this means the RF or radio measurement not timely updated, so it can have less downlink performance. And there is a dynamic. Also, some vendors might support the dynamic CCI reporting. So this dynamic can be usually tuned based on the number of users in the cells. The GNB can decide whether to increase or decrease the duration based on the number of users in the cell. But there is a prerequisite for this part. If the GNB doesn't support dynamic BCH resource allocation, if you remember in 4G you have the concept of BCH dynamic resources, GNB can increase or decrease the dynamic BCH resources based on the usage or the user on that cell. So this is, it can, for example, if it's not supported, probably the changing this duration will not have a real impact on the uplink. And here is the idea about dynamic BCH resource allocation. If you remember in 4G, you used to have this kind of concept that the GNB, instead of assigning a fixed resource of BCH, now it can tune, reduce, increase the BCH resources based on the load on the side. So this accordingly, whenever you reduce the BCH resources, this can increase the BCH. BCH resource will move to the BCH, and accordingly, can improve for sure the uplink throughput. And this is also, it can be depend on the current releases, on the feature and vendors and so on. And that's it for today's video. I hope if you like the contents, to share it with your friends and to press like and to give comments with your feedback. Thank you very much, and see you next video.